So a little addition to this discussion of linear models for those of you who are exceptionally motivated and who would like a little bit more complexity. This is a separate family of models that are called hierarchical linear models or linear mixed models. When do we use them and why are they called mixed and why are they called hierarchical? Let's see. Normally, the general linear model assumes that your observations are independent. Basically, every two individuals in your sample, they don't have anything in common between them, which separates them from any other individual. And this is called independence of observations. In regression, it's independence of errors, and so on. Unfortunately, in real life, this is not always the case. Sometimes we get what is called hierarchically structured data. For example, you have children who belong to the same class at school, and you have in your sample whole classes. So two children from the same class, they share something in common that they don't share with children from another class because they had the same experiences with the same teachers and so on. So this violates the independence of observations assumption. And we discussed not so long ago that this can produce aggregation bias. Basically, in your conclusions, you will see a mixture of effects that are associated with the level of individuals and that are associated with the level of groups. That's why, if we have this kind of data, we are typically trying to separate the variance that is associated with individuals and the variance that is associated with the higher level, the level of groups, for example. And these models are called either linear mixed models, mainly in cognitive sciences, or hierarchical linear models or multi-level modeling in the context of educational and social research. But in principle, it's the same family of models with very minor differences. These models introduce random parameters to account for some differences between our observations. What are these random or variable effects? In a normal model like ANOVA or regression, we have a fixed effect. So we have a single estimate of a regression coefficient for the whole of our sample. Or if we split our sample into groups like males and females, we can conduct a moderation analysis and we will get two regression coefficients for two dummy variables. But these coefficients apply also to the whole sample. The variable effects or random effects, they are estimated separately for each subgroup within our sample or for each group of observations that are not independent. For example, if we conduct a traditional regression, we have two groups and we'll have one single estimate of regression slope. However, if we conduct a random coefficients model, random coefficients regression, it will estimate this slope separately for both groups. And as a result, the estimation of slope will be more precise, more differentiated. When do we have this kind of data? Actually, very often. In educational research, we get students who are grouped within schools. In cross-cultural research, we get respondents from different countries, which are also homogeneous subgroups. In cognitive models, we get observations or trial results grouped within participants. From every participant, we get a bunch of measurements. In family psychology, we get children from the same families. So a family is like a level 2 unit. In organizational research, we have individuals belonging to different teams. So these are all hierarchically structured data. And as we discussed before, if we don't separate the two levels of variance, we get a very blurred picture. We get aggregation bias. And unfortunately, traditional statistics, they don't really do a good job at separating those two sources of variance. So as an example, for example, this is data which simulated data which comes from 5 different schools, the association between socioeconomic status and exam score. If you model just a fixed effects traditional good old regression, you will get one estimate for every school, and you will make an assumption that higher socioeconomic status is associated with higher exam score, and this association is very strong. However, if you use a random slope model, you will see that it's not quite the case. There are schools where this association is fairly strong, but still it's not as strong as this slope that you've seen here. But there are also schools where this association kind of disappears. It can be completely zero. And socioeconomic status predicts how strong is this association in different schools. So basically, the average socioeconomic status of school will predict how strongly the socioeconomic status of a child is associated with exam score. Schools where on average parents are rich, for some reason this association is stronger. In schools where parents are poor, this association disappears because maybe there is more equality and, well, but of course it's simulated data, so don't take it too close to your heart. So if you have this kind of data, what can you do? How can you deal with it? The traditional approach would be to average everything. For example, in cognitive research, if you got several trials from participant, you would just average and you would work with averages for every participant. Or in cross-cultural research, you can average scores for countries and just work at the country level. But unfortunately, you lose a lot of data, your sample becomes very small, and also you cannot, it does not always make sense to average individual level variables logically. Another approach can be to use what's called a sandwich estimator in some statistical packages, where you confine yourself to level 1 analysis, but you cannot include group level variables. A more flexible approach is regression approach, fixed effects approach, when you try to model each group as a dummy variable. So you enter it into regression, and this way you separate the variance that are associated with group membership, and you can also model some interactions in principle. So is this approach bad? Well, not at all. The problem is that when the number of groups becomes large, it becomes completely impractical, because the number of dummy variables, for 50 countries you will have 49 dummies, and all the interactions, your model will become a nightmare. And also, there is a more tricky statistical consideration. If you are using fixed effects regression, it kind of treats your groups as a whole general population. So your effect size estimates are only applicable to this particular sample. If you are using a linear mixed model or hierarchical linear model, and you model this group as a random factor, then you treat those groups as a random subpopulation from as a random sample from a population, and as a result you can generalize your findings to the general population that is not part of your sample. So if you want this, then also fixed effects regression is not the best idea. And there are actually quite a few different multi-level models. I will not really go into very much detail because ideally we would need to take a separate course, but just to give you an idea of what they are and how they work. So we have two levels of information, the level of individuals and the level of groups. And we have some variables measured for individuals and measured for groups. For example, some individual education, and at the team level, maybe some agency variables like the number of people in this group. And when we do multi-level modeling, we start with the simplest model, which basically starts by modeling random intercept, which starts by modeling the mean scores for all individuals as a function of group membership. And then we can complicate this model by adding additional predictors. For example, we can add an individual level predictor. And as a result, we will have a slope of this predictor. Because it's a random intercept model, this slope is the same for all agencies. So what differs across agencies is just the intercept. And in this sense, this model is almost like ANCOVA, because the same slope of association of covariate with the dependent variable, plus there is a factor, which is group. So essentially it's ANCOVA, but it's not quite your normal ANCOVA because it's ANCOVA with random effects. So the estimates will be slightly different. And the conclusions can be slightly more trustworthy. And you can, what is different from ANCOVA? In this model, you can also include variables that are measured at level 2. And this is not something that you can do in regression. In fixed FX regression, if you include some mean scores for country and you assign the same mean score to every individual, or an individualism score for country, and you assign this individualism score to every individual from that country, this will be completely wrong, because this score does not belong to an individual. It only belongs to a country. So in regression, you cannot enter these level 2 predictors into your regression equation at all. And you cannot combine them, obviously, with level 1 predictors. So if you have some level 2 variables that you would like to include, you need a hierarchical linear model. And you also need a hierarchical linear model if you're interested in random slopes. What are random slopes? Basically, this individual covariate predicts some individual level outcome. But the slope of this association can be different in different groups. In some groups it can be strong, in some groups it can be weak, or even maybe negative. So in this random coefficients regression model, you allow this slope to vary across groups. And then you can also try predicting this slope with some other variables, like for example mean education in a country. And if you get this prediction, this is called a cross-level interaction. So I will not go into technical details because it's not so easy to estimate these models in SPSS. I will just show an empirical example to give you an idea of what cross-level interaction is. So an example of this most complicated model 6, when we try to predict the slope of association with some kind of level 2 variable. So this result comes from a study that we were conducting with Joanna Rožička-Tran, our Polish colleague. And the goal of this study was to investigate the association of social antagonism with subjective well-being in different countries. And social antagonism, what is it? It's basically a belief that everyone is against one another. And one of the beliefs that exemplify this social antagonism is called this belief in a zero-sum game. So if you heard speeches of Russian political leaders, they have this very strong idea that countries always compete with one another for resources. So it's not a win-win thinking, it's a win-lose thinking. And it's measured with questions like, if someone gets richer, it means that someone else must get poorer. Or life is so organized that when someone gains, someone else has to lose. So it's an idea of a limited resource as opposed to an idea of productivity. And we explored how this belief is associated with satisfaction with life in different countries. On average, this association is slightly negative. So people who believe that people are all against each other are less satisfied with life. However, the question is, does this association vary across countries? is it the same in different countries or not? And in this study, we tested several models, but the final model which presents the main results is this, which corresponds to model 6 in this David Garson classification that I just showed. It's a random slope model where our slope is an outcome of some level 2 predictor. And here we start by modeling for each country the association between individual belief in a zero-sum game with individual satisfaction with life. So imagine that we take each country separately and we conduct a regression. And the slope for this regression is this random slope. But then we do something more interesting. We try to see if this random slope is predicted by some country level variable. And this country level variable can be anything like GDP or individualism. But here, what is interesting, we took the mean score for the same variable, belief in a zero-sum game. So essentially, we tested the hypothesis, if a country as a whole is a place where people are more antagonistic, are the associations of individual antagonism and well-being the same or different? And here you can see just a little summary of those results, a graph that we had in the paper, which I managed to produce at the time, and a nicer graph that I just did today. So this graph shows basically estimates of this slope across countries. The vertical line is 0, and the slope is standardized. So you can see that this association is generally negative. In about half the countries, it's statistically significant, but in many cases, it's not statistically significant, and sometimes it becomes slightly positive. So this slope is very weak, actually. The strongest coefficient here is about minus 0.10, maybe slightly more, something like minus 0.13. So it's a fairly weak association. However, its variance across countries is statistically significant, suggesting that these differences between different countries are probably not by chance. And in this study, we tried to predict this slope by this social antagonism at the country level. So, for example, in Hungary, if you are antagonistic, you are less satisfied with life. And the same in Chile, and the same in Uruguay, Kazakhstan, and so on. But in countries like India or Vietnam or Latvia, if you are antagonistic, you are not less satisfied with life, and maybe even slightly more, even though it's not significant. So when we plotted this estimated slope, the vertical axis, and the mean belief in the zero-sum game across countries, you can see that there is a clear correlation, and it's statistically significant. In countries where people are more antagonistic, being antagonistic is not associated with a decrease of subjective well-being. And the same we observed for negative affect. There the effect was even stronger, and we had an explanation that maybe in countries where people believe in competition, where people always compete against one another, negative emotional experiences are just part of daily life, and they are not related to satisfaction with life in a negative way as strongly as in countries where people are less antagonistic. So a potential explanation, if you live in a place where everyone is antagonistic, you must also be a little bit more antagonistic, but that probably is not going to have a negative effect on your satisfaction with life, because it's going to be adaptive. Or maybe it will be adaptive in interactions with a larger society, and it might be maladaptive in the interactions with your immediate relatives. So these effects might compensate one another, and that's the reason why this association in those countries is not significant, and it's basically 0. So it's just an example of a cross-level interaction. I hope that you've got the idea of what those hierarchical linear models are and how we can apply them. There are nice books if you're interested in modeling them in SPSS. It's a book by David Garson. If you are interested in modeling them in R or M+, it's Job Hawks, and there are also quite a few other books for R nowadays. It's a little bit tricky because these models have many different parameters, and depending on a single parameter, the whole meaning of the model can change. And it's not always evident what are the defaults for all these parameters. And sometimes you think it's the same model in two software packages, but there are different defaults, and you get different estimates, and you struggle. Yeah, so it takes quite some time to really master it. I can't say I mastered it myself, but at least I tried to apply them a few times. And the main logic here is that you need to keep your model as simple as possible. You start with the easiest possible model, and you introduce the minimum number of parameters to avoid your model from being too complicated, because otherwise it becomes very hard to interpret and to understand. Okay, so we have explored some different linear models today. There are many different linear models, and I hope, as it was clear to you from this example with pretest post-test, that sometimes there are several ways to test the same hypothesis. And it's normally to choose the way that is the simplest, that works best to solve your problem, rather than the most complicated statistic that you want to impress your reviewers. They will not be impressed if your if your problem can be solved using simpler means. And of course, not all relationships in the world are linear. But we are not going to discuss nonlinear models in our course, but if you master linear models and if you have an idea of how they work, it's going to be easy for you to also apply nonlinear models, because the logic is pretty much the same, only it's slightly more complicated. And of course, whenever we apply those linear models, we always need to be aware about the limits within which our model remains applicable, within which we can extrapolate it. Otherwise, we might end up like this guy in the picture. Okay, so as the source of information, I totally recommend the wonderful textbook by Tabachnik and Fiedel. And good luck in exploring linear models. See you soon for a discussion of multivariate methods. And we'll explore factor analysis, cluster analysis, and some other nice tools. So thank you for your attention today. See you soon.